Okay, we are looking at chapter 4.1 to 4.3 today. The focus is going to be solutions. Another term for solutions is homogeneous mixtures. That means everything is in the same phase and everything is dissolved within the solvent. So there are two components of a solution. First component is the solvent. The second component is the solute. Our focus for the solvent is going to be water. If water is the solvent, that means we are looking at aqueous solutions. So remember, when you've looked at different chemical reactions, for example, hydrochloric acid plus sodium hydroxide reacts to form sodium chloride and water. Remember the states of matter that are the subscripts next to each one of these compounds. Here, here, and here we have AQ. Those are all aqueous solutions. So in this case, it's hydrogen chloride gas dissolved in water. In this case, it's sodium hydroxide solid, then dissolved in water. And in this case, it's sodium chloride dissolved in water. So how does water react with both covalent and ionic substances to dissolve them? Right? A homogeneous mixture means all of the components are in one phase, which means the solvent has solvated the solute. It's dissolved the solute. So here's water. Now there's two important properties or characteristics of water which give it an overall important property. The first one is that there's an uneven charge distribution. And it's bonds between the two atoms which are bonded. So between hydrogen and oxygen, there's an uneven charge distribution. And second is that it has a bent shape. Both of these together add up to make water a polar molecule. So what does that mean? It means that one side of the water molecule is partially positive, and that would be down here by the hydrogens. The side is partially positive, and up top there's a partial negative. This delta just means partial. Okay, so it's not fully negatively charged. Partial negative on top, that we see on top, partial positive on the bottom near the hydrogens. So then how does water interact with itself? How do water molecules within something like liquid water or solid water interact with itself? So let's remember, down here we have partial positive charge. Up top we have partial negative. We'll look more at why the oxygen is partially negative and why the hydrogen is partially positive when we get closer to chapter 10. Okay, so another water molecule will interact with this water molecule like so. And then another one. And we can draw more many water molecules. Okay, why is that? Because the partial positive ends of each water molecule are interacting with, the partial negative end of the water molecule. So notice there's a nice interaction, right, between each oxygen and hydrogen. I'm just drawing little dots to show their interaction that they're having, favorable interaction. So this brings us to how something like an ionic compound would have a favorable interaction with water. So how does something like sodium chloride interact with water to become dissolved? So if I start with solid, and I have liquid water, and then I have dissolved sodium chloride in water. How does that happen? Well, let's look back at a water molecule and again draw its partial positive end and partial negative end. And let's think of how sodium chloride is bonded together and why a sodium ion would be attracted to a chloride ion. So remember that sodium is positively charged and chloride is negatively charged. Okay? Ionic compounds, remember, exist in a lattice structure, so there's many sodiums and chlorides within this framework. But let's just focus on how each ion interacts with each other. So remember, again, sodium's positive, it's a cation, and chloride's negative, it's an anion. So they have an attraction to each other because of their opposite charges, right? So when sodium chloride goes into water, let's take this away. When sodium chloride gets put into some water, what happens? Well, it ionizes. Okay, what does that mean? I'm going to write this. It means that it exists in its ion form. Now, why? Because remember, again, that water has an uneven charge distribution. Therefore, the sodium will interact at the negative, partially negative end of the water molecule, whereas the chloride will interact with the partially positive end of the water molecule. And it will actually look something like this. If I looked at one sodium ion, water molecules would orient themselves around this sodium ion to form what's called hydration shells. Hydration shells. The sodium is then solvated by the solvent, which is water. Okay, you can imagine the exact same thing happening with chloride. Remember, chloride being negatively charged. So which ends would interact with the chloride ions? Well, you would have the partially positive ends of the water molecule interacting with the chloride ion. And those would also be hydrated or solvated by water. So let's ask, what we focus on so far is just ionic compounds. So do all ionic compounds dissolve or become solvated by water? Because we know all ionic compounds are composed of what two things? Of a cation, positively charged, and an anion, negatively charged. Well, if all of them are composed of a cation and an anion, wouldn't all of them have a favorable interaction with water and thus become solvated? Well, the answer, you could probably guess by the way that I'm asking the question, the answer is no. Not all ionic compounds dissolve in water. So the follow-up question would then be why? Why do they not all dissolve in water? Well, if we look, for example, at something like lead 2 iodide, remember your naming, just as a reminder, lead 2 iodide, the lead, 2 positive, right? And the iodide ions have a much stronger interaction than they would with water. So if lead 2 iodide were to dissolve in water, you would have the negative end of an oxygen interacting, or the negative end of a water molecule, which is the oxygen, interacting with the positively charged lead, right? Well, that actually doesn't happen. Okay, so I'm going to put a big circle X. This does not happen. These stay intact. So the general qualitative answer to why is some ionic compounds have a greater or stronger attraction between the ions than they would have with water. So how can you predict this? Well, you would actually have to do some testing. That is what we have the solubility chart for. So the solubility chart, or the solubility table, is used to determine if an ionic compound is soluble. You can also determine, if you're looking at a chemical reaction. So say you're looking at a reaction and you see in the notation as the subscript, you see AQ. This right here indicates that sodium chloride is soluble, so in water. So the notation, let me fix this. AQ equals soluble. You can remember that. If you see something like, for example, a reaction that has lead 2 iodide and you see solid, okay, and it's taking place in water, this reaction is taking place in water, then you can conclude that lead 2 iodide is insoluble. So if this reaction, let me close that, is taking place in water and you see that S, that means solid, therefore S is telling you that that compound is insoluble in water. From this, let's take a look at some of the downstream effects that dissolving an ionic compound in water has. So if I were to look at a lattice structure of sodium chloride, okay, this is just a very primitive, it's not actually what sodium chloride looks like, but okay, we have some lattice of sodium chloride, and then I also have next to it, a little beaker of distilled water, okay, DI water, and this is just a lattice of table salt, say of salt. Great. So if I were to actually attach electrodes to each of these, so if I put in a little probe to basically measure the conductivity, how the flow of electrons travel, how strongly they travel through these two components, this lattice of salt and DI water, you would essentially see zero ohms. Okay, no conductivity. There's very very little flow of electrons through these two, but when I actually mix them, so let's say I put the sodium chloride into water, into this water, I take my little salt shaker, I salt it into water. What I end up with, right, is ions. Sodium ion, chloride ion. Well, this dramatically increases the conductivity. So if I were to put a conductivity probe in here, you would see a very high reading of ohms. Okay, so it can power a light bulb, right? So the electrons can flow through this solution, and this is what we call a strong electrolyte solution, because I have an ionic compound. So right here I have an ionic compound that when it goes into water, it completely ionizes. So it's the presence of ions in the solution. Whoops, ionizes. Okay, so how do I count for these? And notice we haven't moved on to covalent compounds just yet. So how do I account for the amount of ions that are actually in my solution? So let's continue just to focus on sodium chloride. Let's say I put 1 mole of sodium chloride into water. The question is, how many moles of ions yielded? So let's look what actually happens. We know that when sodium chloride goes into water, solid sodium chloride, I have 1 mole. When it goes in H2O, it ionizes, right, to sodium plus and chloride minus. Now notice it's a 1 to 1 to 1 mole ratio. So look at the stoichiometry here. Therefore, I yield 1 mole of sodium cations and 1 mole of chloride anions. So total moles of ions is 2. You see how that happened? So let's look at a different one. Let's say we had sodium sulfate, and we put that into water. And make sure that this balances, right? I want it to balance on both sides. So on the right side, I would have 2 sodium ions and 1 sulfate anion. And let's make it a little bit more difficult. Let's say I started with 0.50 moles of sodium sulfate. Well, let's actually write out the equation. Let's write out the equation stoichiometrically. So if I start with 0.5 moles of sodium sulfate, and let's say my question is how many moles of sodium are yielded. I would go up here, say, well, I started with 0.5 moles, and I know that there's 2 moles of sodium cations for every 1 mole of sodium sulfate. This cancels. I would end with 1 mole of sodium ions. So really, I'm writing out the equation showing the ionic compound being ionized, and I'm balancing to make sure I match the number of ions I originally had, and then I'm setting up a very basic stoichiometry problem. So when you think about covalent compounds, on the other hand, you're thinking of things like sugars. We're going to use, let's say, sucrose, for example, or you might be thinking something like ethanol, antifreeze, things like that, things with a lot of carbons and hydrogens and oxygens often. Okay, so let's think something like sugar, like sucrose. So I'm just going to say generic sugar. When I put that into my beaker of water, what actually happens? And sucrose is C12H22O11. When sucrose goes into water, does it ionize? Well, the answer is no, it does not ionize. So then the question is, how does it dissolve? Because you know that when you put sugar into water, as long as you don't put too much, that it can, if you stir it around, it'll dissolve into the water. So how does it dissolve? Well, the answer is because sucrose has these OH bonds, just like water does, and these OH bonds are very polar. They're polar bonds, which means just like in water, there's a partial positive end and a partial negative end, which allows the water to also make contact with the different ends of the sucrose molecule and solvate it as well and dissolve it into water. But no, it does not ionize. So since it does not ionize, since sucrose and other covalent compounds, for the most part, don't ionize when dissolved, in water. They are then, they do not make electrolyte solutions. So therefore they are classified non-electrolyte solution. Let's say a non-electrolyte solution is yielded. So that means that these compounds do not conduct any electricity. They do not conduct a current. And just as a reminder, remember that an electrolyte is a substance that conducts a current when dissolved in water. So although sugar dissolves in water, it doesn't actually conduct a current. So for the most part, we can categorize covalent compounds. Oops, that is not how you spell covalent. Covalent compounds and ionic compounds mostly as non-electrolyte solutions and ionic as electrolyte. Now there is a degree of strength in all electrolyte solutions, in all solutions, of their ability to conduct electricity or to conduct a current. And so when you're in lab, you will be classifying as solutions as non, weak, or strong electrolyte solutions. And we'll go over how to do that in experiment 4. Now there is an exception for covalent compounds. The exception is acids. And we will also categorize acids into 2 categories, and that will be strong and weak. Strong acids will also be strong electrolyte solutions. They will make strong electrolyte solutions. And weak acids will make weak electrolyte solutions. So that is an exception to keep in mind. Okay, so let's now talk about expressing concentration in molarity. Concentration is the amount of a substance that you have per the whole that is present. In this case, when we're talking about molarity, we're talking about the moles of solute per liter of solution. So let's pick an example. Let's say we have something like sodium hydrogen phosphate. So we'll say our solute is sodium bisphosphate, and our solvent, we're going to be sticking with water. And let's say I dissolve 1 mole of sodium hydrogen phosphate in water to make 1 liter of solution. How would I calculate the molarity? So there's a couple of different ways I can notate this to ask for the molar concentration of sodium hydrogen phosphate, I can ask, I can put brackets around the solute with a question mark. That's asking what the molar concentration. I could just ask, what is the molar concentration of solute present in solution. Or I could ask, what is the molarity? So I just want you to be comfortable with the various ways that I could ask the question. Okay, so if we look at our molarity equation, again, we know that molarity is equal to moles of the solute over liters of solution. Okay, so I'm going to drag this down here. Moles of solute. The solute is sodium hydrogen phosphate, and I have 1 mole, so that's simple. Over liters of solution. What is the solution? As a little reminder, the solution is the solvent plus the solute. So molarity is asking for the moles out of the total volume that I have. So my total volume is 1 liter, because in the problem I told you that you made 1 liter of solution. Therefore, the molarity is simply 1.0 big M. Big M, again, just means molarity, right? This right here is just big M, and big M has units of moles per liter. Those are the units that you have. So molarity can be used as a conversion factor. What do I mean by that? I could ask the question a different way, or I could ask a different question, yet still utilizing the conversion factor of molarity. So let's say I told you you have 200 milliliters of a 0.25 big M, that means molar, solution of potassium bromide. And I asked you, so this is an example, how many moles of potassium bromide do you have? So pause the video, take a second to look at that, to see if you can actually solve for that without me leading you down that path. Okay, so like I've said before, we always write down what we're given in the problem. So I have 200 milliliters of a solution. So I'm going to put potassium bromide solution. And then down here, so again, this is what you have. And then I'm going to write down given information down here. So I have a 0.25 molar solution. And what I want is moles. Oops. Okay, so my suggestion is every time you see big M, you write it as 0.25 moles over liter. You always write that when you see big M. This way you will notice that you have moles and liters, and you want to get to moles, so all you need to do is get rid of liters. Well, how to get rid of liters? Well, I've started with milliliters. Now you want to ask yourself, is there anything given in the problem that I can cancel out milliliters? Well, not directly, but I know since molarity is moles over liters that I should convert these milliliters to liters. I know there are 1,000 milliliters for every 1 liter. That will cancel out milliliters. Now I can use molarity as a conversion factor. Okay, so I'm going to place it so that liters is going to get canceled out. Moles will stay on top. So liters get canceled out. Mole stays on top. And you should have gotten 0.050, 2 sig figs. There's 2 in molarity, and there are 3 in the volume. So I have 0.050 moles of potassium bromide. There are other questions that I could ask you. So let me just give you another problem that you can try. You pause this and try it, and then come back to see the answer. So let's say that I said you have, let's say 35 milliliters of a 0.125 molar solution of zinc fluoride, and I want to know how many moles of ions you have. Oops. I want to know how many moles of ions you have. So ions do you have, and how many grams of fluoride ions do you have? Okay, so pause the video and then come back to see the answer. Okay, so here we have the answer. Let's look at A first. So we're paying attention to A. So we start always with what is given in the problem. You have 35 milliliters, so I wrote that down first. Whenever I see a molar concentration in big M, remember you should always write it in its expanded units, which is moles per liter. Okay, so I know that in order to cancel out milliliters, what I was given, I have to convert it first to liters. So that's my first conversion. It cancels out my milliliters. Then I can use my molar concentration here as a conversion factor, making sure I put liters on bottom so that liters cancels. Now the next step, remember the question is asking how many moles of ions, so that's where you have to look at the compound that's given and decide when it dissociates in solution, how many ions are actually yield from that dissociation, from that ionization. So I'm going to write it down here. When zinc fluoride solid goes into water, it forms 1 zinc 2 plus. How do I know that? Because the subscript here for zinc is just 1. That's aqueous. Plus, and the subscript next to fluoride is 2, so 2 fluoride ions. So together I have 1 zinc and I have 2 fluoride, so I have a total of 3 ions, 3 moles of ions that are formed for every 1 mole of zinc fluoride. and that'll cancel out my moles of zinc fluoride, and then I'm left with 1.3 times 10 to the negative 2 moles of ions. Okay, so moving on to B. Again, I'm going to start with what I'm given in the question, in the problem. That's 35 mils. I cancel out those mils to get to liters because I am going to use this conversion factor, my molarity, in moles per liter, in order to cancel out liters of solution. So let's look back at what B is asking. How many grams of fluoride do I have? Okay, so now I have to get rid of moles of zinc fluoride, but I can't go directly, remember I can't go directly from moles of one substance to grams of a different substance. So first I have to go to moles of that substance, which would be moles of fluoride. So I use this conversion factor here. I know there are 2 moles of fluoride for every 1 mole of zinc fluoride because I have a 2 in the subscript. So that's going to cancel out moles of zinc fluoride. Great. And then I'm going to just use my molar mass for fluoride here as a conversion factor, grams per mole. I get this off the periodic table. And there are 19 grams of fluoride for every 1 mole. And everything else will cancel out. I'm left with grams of fluoride in my answer. So check to make sure that, check this against what your work is and mark down anything, any discrepancy that you observe, and make a little note to yourself about it. Okay, on to the final section of 4.1. Since we've learned so far what a solvent is, what a solute is, how the two come together to form a solution, now we've learned how to calculate the moles per liter, the molar concentration of that solution. We've also learned how to calculate the grams of solute in that particular solution. Now we're going to learn how to prepare a solution or how to dilute that solution. So here are the steps that you'll take in a laboratory to prepare a particular solution. First thing you're going to do is mass the solid. You'll then transfer the solid to the appropriate container. You'll dissolve the solid into the solvent, and then you'll add, not solid, you'll add solvent. Let's change that. You'll add solvent to the final volume. So let's change that. You'll add solvent to the final volume. Great. So let's look at an example. I'm just taking this directly from the book, from the Silverberg book. Okay, so let's say you're tasked with, you want to make a 0.500 liter of 0.350 molar concentration nickel to nitrate. And, it's actually nickel to nitrate hexahydrate. And you need to explain to me, since you're actually not showing me how to do it, you're going to explain how to prepare this solution. So keeping the steps in mind, I want to mass the solid, right? That's my first step, is to mass the solid. Okay, in order to mass the solid, I need to know what mass of the solid I need. So really step 1 is the only step that you're doing calculations. Every step thereafter is the calculations are finished for you and they are just hands-on. Okay, you're not doing any calculator work, paperwork. You are just taking the solid that you need, dissolving it, transferring it into the desired container, and filling it to the final volume. So it's really step one is where all the calculations take place. So again, I'm going to write down what I have. I'm given a 0.5 liter solution. It's already in liters. Then I'm going to write down my molarity. Down here I'm going to write my molarity is 0.350 moles of nickel 2 nitrate. This is why you really have to have a mastery of naming compounds, because it gets tricky. You're not able to solve for molecular formula or molecular weight if you don't know the molecular formula of the compound. Hexahydrate. Okay, great. Per, this is really long, liter of solution. Okay, so I'm going to plug that in here as my conversion factor. Remember, I want you to write out all the units associated with numbers because this really will minimize the amount of errors that you make. So I'm going to put 0.350 moles. I know this is super long and it takes so much more time to finish, but it's really going to benefit you in the long run. Over liters of solution. Great. That cancels. Okay, so step one is finding the mass of the solid, right? Well, right now I have moles of the solid if I were to compute this. So I'm going to calculate the molar mass of nickel 2 nitrate, hexahydrate, which I've already done, so I'm just going to put that down for you. 290.82 grams of nickel 2 nitrate, hexahydrate. So for those of you who are wondering, yes, the hexahydrate right here does get added into the molar mass. So you do need to find the molar mass of water, multiply it by 6, and then you add that to the overall molar mass of nickel 2 nitrate hexahydrate over 1 mole nickel 2 nitrate hexahydrate. Okay, let's make sure these cancel. I'm left with grams. If I compute this, I'm going to kind of quarantine this off by itself so it doesn't get mixed in with our calculation here. This will give us 50.9, 3 sig figs. I was given 3 and 3. So 50.9 grams of nickel 2 nitrate hexahydrate. All of these calculations are very, very similar. So again, what I want you to remember is that you want to convert to liters if you're not already given liters for the volume. And then I also want you to expand this big M into moles per liter. So if you see that big M for molar concentration, write moles per liter so that you can use it as a conversion factor. Okay, so what do we actually do with this? So step one, remember, is mass the solid. So I'm going to write down my steps. I'm going to first mass out 50.9 grams of nickel 2 nitrate hexahydrate. The second step, we look back at our steps, is to transfer the solid. Okay, where are we transferring it? Well, it says we want 500 or 0.5 liters, which is the same as 500 milliliters. And you've used a volumetric flask in lab, so I'm going to just draw a little picture here. You have this volumetric flask. Okay, pretty shoddy drawing, but I'll label it as my 500 milliliter plus or minus 0.02 milliliter volumetric flask. Has a line right here. So I'm going to transfer the solid, this is going to be my solid, into the volumetric flask, but I will add something. You should have some of the solvent already in your volumetric flask. To dissolve the solid. So I've transferred solid into container with some solvent. Then I'm going to dissolve the solvent, the solute, sorry. And you're going to add solvent as is necessary to get any remaining residue off of the neck of the volumetric flask. Okay, so I'm actually going to make sure it goes all the way down to the bottom and then it's completely dissolved. You don't see any solid down here. It's a homogeneous mixture. And then I'm going to add solvent to desired volume. And remember, this line right here is what indicates the desired volume. You want to make sure that the bottom of the meniscus hits that line. And that's how you're going to make a solution in lab. So how do you take this solution maybe and dilute it? What does diluting actually mean? Diluting is lowering the overall concentration, molar concentration of the solution. So remember, let's bring this up. Remember again that big M equals moles per liter. So if you're diluting a solution, you are increasing the liters so that the overall molarity goes down. Really, you're adding solvent to the solution. You're adding solvent to increase the liters and decrease the molar concentration. So let's say I took this solution that I just made. So I just made a 0.500 liter solution of 0.350 molar concentration of nickel 2 nitrate hexahydrate. But let's say, so I have this, let's say I want 200 milliliters of 0.150 molar solution of nickel 2 nitrate hexahydrate. Okay, there's a two-part calculation that can be combined into a dilution formula. Looks like this. You might also see it as M1V1 equals M2V2. What I have originally written is M diluted times V diluted equals M concentrated times V concentrated. There's many different subscripts that you could associate with the molarity and the volume, but typically you'll see it in one of these two fashions. So let's plug in, and let's learn how to plug in the numbers that we have with this formula that I have just written down. So I have a 500 or 0.5 liter solution of 0.350 molar concentration. So that's my M concentrated and V concentrated. So I'm going to plug that in. M is molarity, so I have 0.350. Again, I'm going to write moles per liter. In this case, I'm not going to have you write down nickel 2 nitrate hexahydrate because you're dealing with the same solution throughout this problem. It's not going to change. And then instead of plugging in the volume that I have, I'm leaving this empty. Now, why am I leaving this empty? When you're diluting a solution, you are taking part of, let me draw this, you're taking part of the original, so this is your original, you have 0.500 liters of 0.350 molar solution, and you're diluting, in this case, into a smaller volume. Let's say I have a smaller volumetric flask. And you want $200. I'll put a little decimal place after the 200. I'm making this problem up so I can determine the amount of sig figs I want of a 0.150 molar solution. Okay, I am determining how much volume I actually want to take from the original and place it into the diluted concentration or the diluted solution. So I'm not going to take all 500, okay? That would give me the same solution at the end, right? I only want to take some of the 500, place it into the new vessel, and then add solvent. In this case, we'll say water's our solvent until I get to the desired concentration. So that's why I'm leaving this volume blank. Okay, so now I'm going to plug in M diluted. So the diluted molarity that I want is 0.150 moles per liter, and I want 200 milliliters. Now I'm gonna convert this into liters, so my liters cancel out, and I've already done that right here. I'm not going to show you that conversion because you should know that there are 1,000 milliliters per 1 liter. So I'm going to put 0.200 liters, and I'm going to compute that. So I'm going to solve for V concentrated. That's going to equal 0.150 moles per liter times 0.200 liters all over 0.350 moles per liter. You'll notice that moles and moles will cancel. These 2 liters will cancel. This is the denominator, right? It's on the bottom of a denominator, which makes it a numerator, okay? That makes it the top unit. Okay, so I'm going to scroll this up, and we're going to compute this. And I have 0.0857 liters of original solution. Okay, so I've solved numerically. Now what does that mean? That means I'm actually taking, I'm going to write it right here, I am taking 0.0857 liters of the original solution. I'm placing it into my new flask, and then I'm filling to the desired volume, which is this line, to make a 0.150 molar solution. So what am I solving for? If I'm actually diluting a solution, I'm solving for the volume of the original concentrated solution that I need to take in order to make the diluted solution. Okay, let's put this in milliliters so we know. This is the same thing as saying 85.7 milliliters will be taken over. And so I'm going to add roughly 114.3, a little bit more. I'm adding water until I hit the desired line on the volumetric flask. Great. That is the end of 4.1. I'll have a separate posting for 4.2 and 4.3. This is the longest portion, so the next part will only be about 20 minutes. So click on the link in Canvas for the next 2 sections in order to be prepared for lab number 4 and number 5.